All right. Everyone's notified. I'm going to grab a pen. I'll be right back. All right, everyone. Welcome to day 2. I left off day 1, problem 22, as I recall. I'm going to pick up problem 23, and we'll go from there till the end. 23, use the given information to sketch the graph and fill in the table. Okay, see, we have the f of minus 3 is 0, so we have a critical point at x equal to minus 3 and at x equal to 4. Those are two places where the first derivative is 0, where the graph is perfectly flat. We also have an inflection point, places where there's no concavity, where the second derivative is 0, at x is minus 3 and at x is equal to 1. Notice at minus 3 we have both a critical point and an inflection point, a place where it's perfectly flat and a place where it changes concavity. Fill in the... So here we are in the first table. There's 3 spots on that one. Since plus, plus, minus, we should have increasing, increasing, and decreasing. Of course, you won't have anything to fill in on the final exam because it is multiple choice. But still, you have to know. First derivative is positive, it's increasing. First derivative negative, it's decreasing. The second table is a minus, a plus, and a minus. So that would be concave down, concave up, and concave down. So the graph goes concave down, concave up, concave down. It goes increasing, flat, decreasing. Let's see if we can sketch a possible graph of that function. Well, one thing we're not given on this is points. We're not given any points whatsoever. So we can start this graph any place we want. And I'm going to rely on my first table to get this graph started. It's increasing and then it's increasing again. So it's increasing until we get to minus 3. All right, so I'll draw it increasing. I'm just going to sort of sketch in something rough for now. It goes perfectly flat at minus 3. The first derivative is 0. It increases after that until we get to x equal to 4, 2, 3, 4, till we get right to there, and then it starts decreasing. Okay, at 4, it also goes absolutely flat. So there's my critical point. There's my other critical point. Again, you could have started this lower or higher. It doesn't matter. We're not given any points at all. All we're given is that it's increasing, flat, and decreasing. Now we're going to put the curvature in. It's concave down until we get to minus 3, and it's flat here at minus 3. So this sketch should be pretty easy. Want to draw a graph that's increasing and concave down. I want it to be perfectly flat there. Between minus 3 and positive 1, so I'm going to sort of aim for that point there. It's concave up. Okay, now I'm going to draw a graph that's concave up. Lose my little straight line thing here because that's not the graph. Still looks pretty good. Now after this, I'm going to hit that point, of course. There's my little relative max. but it's concave down from here on out. So I switch the concavity, make it go concave down. Hit that point up there, and off I go. So I think what's likely to be given on the final exam is those two tables, and then you have 4 choices of graphs, which one fits the best. 24, find all critical points. Critical points are where the first derivative is equal to 0, at least in this class. So critical points are where the first derivative is 0. I think I did this derivative a while ago. I don't remember for sure, but there was either this one or one just like it yesterday. Let's take the first derivative. First derivative requires the product rule. The derivative of x squared is 2x. Bring that one straight down. Plus, keep that one exactly as it was and multiply it by the derivative of e to the x, which is e to the x. Now our goal here is to find critical points, is to find a place where the slope is equal to 0. And since I have a complicated thing there set equal to 0, it's easiest to solve that if we factor it. So let's see what we can factor out. They don't both have a 2, they do both have an x, and they do both have an e to the x. So we'll factor those terms out. Let's see, this one is just missing the 2, right? 2 times this restores the first sign, plus. The only factor this one is missing is the x. And as always on factoring, I like to multiply through, distribute back through, and see if I get what I started. 2 times x times e to the x times x times e to the x. I like it. Now the benefit of having factored forms set equal to 0 is the only time a bunch of factors multiplied together can give you 0 is if one of the factors is 0. So let's go through piece by piece. One of the cases is when x is 0. If you plug 0 in here, you get 0 times 1 times 2, 0. E to the x, if you remember the graph of e to the x, it looked like that. It never came down and touched 0. And then when is 2 plus x equal to 0? When x is negative 2. Now the critical points, they're points on the graph. They're places where the graph absolutely flattens out. So let's find them, shall we? If I plug 0 into this formula, I get 0 squared times e to the 0. 0 times 1 is 0. There's an ordered pair on the graph of this function. It's 0, 0. What do I know about it? I know the graph is perfectly flat there. Now let's plug in negative 2. If I plug in negative 2, I get 4 times e to the minus 2. That's 4 over e squared. I don't know exactly what that is. E is 2.7, so maybe that's, let's see, 3 squared is 9, 2 squared is 4, probably around 6 or so. So I have an ordered pair, negative 2, somewhere around 6. The graph goes flat there as well. That's what I conclude this problem. I used to go on and find the inflection points, but boy, the second derivative got really messy here, so I took that out. Use the results of problem 25 to make a chart that shows the interval where the function is increasing and decreasing. Okay. Let's see, I have to save my second derivative. I'm going to save it in factored form because that makes it a little easier. And now here I go to find out where this function is increasing and decreasing. The only thing I know for sure, based on my graph here, my 2 ordered pairs, is it has to decrease from -2 to 0. Let's see if we can come up with a all-around game plan for this one. So I'm going to start out with the intervals that this graph is defined. It's defined all over the place. So the intervals in question here will be in between the critical points before and after. First interval will be from negative infinity to the first critical point, negative 2. The second interval will be between the 2 critical points, negative 2 to 0. I've already assumed that it's declining there, or decreasing there, and then the last one would be from 0 to infinity. We want to now find a test point. Any number in these intervals, I'm going to choose the easiest one possible in each case. Now here's where sometimes students got a little confused. We want the value of the first derivative. So if I plug in a -3 in my first derivative. This is -3 e to the -3 times a -1. That's 3 over e cubed. That's positive. So the function is increasing until I get to that first critical point. Now in between -2 and 0, I'm going to plug in the number -1. If I plug -1 here, I get -1 e to the -1 times 1. That's -1 over e. That's a negative number. Therefore, the function, as I figured before, is decreasing until we get there. Okay, now let's see what happens on that last little bit. Again, I don't know anything about the concavity here. I'm just doing some sketching. Now we're going to choose the number 1, put the number 1 in here. We get 1 times e to the first times 3. That again is a positive number. So my bet is there's probably an inflection point someplace in there. It doesn't come to any point, so I can't imagine anything else could happen. The other thing that could happen is this could have an inflection point there, or we could have an inflection point going the other way. So this in no way is an accurate graph, but it does have this critical point and it has that critical point. So decreasing, increasing, decreasing. Find all inflection points on the next graph. So rather than trying to find the inflection points on this function, which required a lot of calculus and quite a bit of algebra, we just sort of start over on the next one. I remember a question nearly identical to this one on exam number 3. So the intervals where it's concave up and concave down is where we're going to go for part B. Let's find the inflection points, the place where it has no concavity. Let's find those first. I'm going to start by finding the first derivative. I'll do that rather than writing the problem up. How about a nice 3x squared plus 12x plus 12, taking the derivative of the f of x function. Now the second derivative yields 6x plus 12. Let's set that equal to 0. X is -2. So there's only one inflection point on the graph. We know it has a y value, we know it has an x value of -2. Let's plug that back in and find the ordered pair. So -2 cubed would be -8. Again, I'm plugging this back in the original. That's where we get points on the graph. -8 plus, that would be 4 times 6 is plus 24. Plug in -2, and the next one is -24. Oh, that's handy. And then -4 at the end. So it comes out to be -12. There is the ordered pair for the inflection point. That's a point on the graph that has no concavity. It's neither concave up nor is it concave down. So now let's see what happens before this inflection point and after the inflection point. Let's see where this graph, for which intervals this graph is concave up and when is it concave down. So again, I'm going to list the intervals here. There's only one critical point. It has an x value of -2. So we'll look at all the numbers before that and all the numbers after that. Like last time, we'll find a test point. -3 and 0, I guess, are two adequate ones. And now I need the value of the second derivative. Okay. So I plug this in the second derivative. If I plug in -3 in here, I get -18 plus 12. That's -6. That's a negative number. If I plug 0 in here for x, I get 0 plus 12, which is 12. That's a positive number. So now my behavior is well defined. Concave down, concave up. Find the absolute max and min on the interval from there to there. Okay, great. So I have the two walls set up at -3 and 0. Sometimes the max and min are at those endpoints, and sometimes they happen to fall in between those endpoints at a critical point. Really, those are the only points I need to test. I need to test both end points, and I need to find any critical points in the interval in question. In this case, it's the interval in between -3 and 0. So I might need a little help out there in YouTube land on this one. I'm going to do my best to plug these numbers in. I'd appreciate a little help on some of these as well. So someone tell me what f of -3 is. I think that's a little bit beyond what I can do mentally. F of 0 I can do, that's easy enough. So that's where I would start this problem. I plug in the left endpoint, plug in the right endpoint, and see what we get. Again, if someone would plug in the -3 there and let me know what you get, I'd appreciate it. Maybe a couple of people, that way we can have a test on that as well. Now I need to find if there are any critical points in between -3 and 0. If there aren't any critical points between -3 and 0, the function is always increasing or always decreasing. The max will be at one endpoint and the min will be at the other. So let's find the critical points. Critical points are when the first derivative is 0. So I'm going to write down here the first derivative. 8x cubed minus 20x squared minus 12x. That looks good. I'm going to set that equal to 0 and solve. And again, it's easier to solve the equation if it's factorable, and this one is. I could pull out a 4 and an x, be left with a 2x squared minus 5x minus 3. Two factors of -6 that add up to a 5 tells me that this is also factorable. 4x, one of these must be a 2x, one must be an x. We need to have a 3, I guess, back here, and a +1 there. So here are my critical points. X equals 0, that's when that's 0. X equals -1/2, that's when that's 0. And x equal to 3, that's when that one is equal to 0. So of those 3 critical points, there's only one that's in the interval from -3 to 0. Oh, this is really going to take some work on some of our parts. We need to calculate f of -1/2. So we have to figure out what that one is. Again, that's the only critical point of these 3 that's in between our 2 endpoints. And we need to calculate f of -3. So out in YouTube land, some of you work on the top one, some of you work on the bottom one. Let me know what values you get for f of -3 and for f of -1/2. As you're working through that, I'm going to double check my calculus and my algebra. Yeah, I like it. So my calculus looks good, my algebra looks good. All we have left to do is evaluate my original function at those 2 endpoints. And if you don't recall what it was, I'm still waiting for cooperation on this one. Okay, I got 293 for this one. Okay, good. This seems to ring a bell. But again, I haven't looked at this one since last December, I guess, maybe? Thanks, Tommy. .45 for the other one, okay. I have a feeling that one came out negative, and I'm not sure why I thought that. But That was my best recollection. Was the middle one was slightly below 0. And there's all sorts of places where you can throw that. Got that as well. Interesting. Huh. All right, I'm going to maybe take a quick look at this sketch of that one, because that's, I mean, there's a critical point, unless it was a case where the critical point was also an inflection point. So let me do a quick graph sketch on that one, just to make sure that I'm getting what I want. So 2x to the fourth, 23rd x cubed minus 6x squared. Looks like my signs are right. And I'm going to set the range from -4 to 1. And you got a y value that was pretty big there. So let's make this y value stretch up to 300 maybe, see what happens. Oh, got it. Now I see what I did wrong. Duh. I was looking at the wrong problem. F of 0 is 5. I was looking back on problem 26 instead of problem 27. So I plugged in 0 and I did it wrong. All right. So I was fairly sure that the minimum point was close to 0, it wasn't 0. So now I can go and answer the questions, find the absolute maximum value in that interval. Max is 293. It is not -3. The min value in that interval is 4.45. It's not -1/2. We want to know the biggest number in this group and the smallest number in that group. And that caused some concern on exam number 3. Ernie and Bert are selling tickets to an event. Oh, I think I saw this one on one of our activities. I think it was Ernie and Bert on that one as well. Let's see if we can figure out how they should sell their tickets, what price they should set for their tickets to maximize revenue. If they price their tickets at 20, they'll sell 1,000. So let's see, $20 a ticket times 1,000, that would be $20,000 of ticket revenue if they make no changes. Every time they reduce the price per ticket by $2.50. Okay, so here's the price per ticket, 20 minus 2.5x or 2.50x if you wish. That'll result in, let's see, if we decrease the price, the number of tickets is going to go up. More people can afford them. And how much were they going to go up by 100 tickets? So there's the revenue function, price per ticket times number of tickets. That's the function that we wish to maximize. We'll maximize it the old-fashioned way, take the first derivative and set it equal to 0. Well, before I take the first derivative, let's multiply this out. There's 20,000, that's that 20,000 I started with, 20 times 1,000. Doing the outside part, that's 2,000x. Doing the inside part, that's minus 2,500x. And sort of, if you would please sort of catch my algebra as I go through. Every once in a while I do something wrong on this. Minus 250x squared. So let's see, I could combine those two if I wished into minus 500x. Let's take the first derivative and set it equal to 0. R prime is negative 500 minus 500x. If I set that equal to 0, I get minus 500 is 500x, and x is equal to minus 1. So I shouldn't make a $1 decrease in price. I should go the opposite way. I should have, I'm sorry, one of those decreases in price. I should go the opposite way. By the way, the second derivative here, R double prime is negative 500. It's a function that's always concave down. So I have a graph that looks like that. It has a max value right there at x equal to minus 1. Now I'm going to go back and answer the question that was posed. And the question posed was, how should they price their tickets? That's what everyone wants to know. Where should I set the ticket price to either maximize my profit, or in this case, maximize my revenue? So I'm going to calculate R of negative 1. That's going to be 20 minus 2.5 times minus 1. That would be 22.5. That's where they should price their tickets. There's the price per ticket. Let's, just for the heck of it, let's figure out how many tickets are going to be sold then. If this is a minus 1, they'll sell 900 tickets. And if I multiply 900 by 22.5, it better come out higher than that original 20,000 that I looked at before they changed any prices. So this is how I like to check my work to make sure I haven't totally messed it up. And that doesn't represent a huge change in price, so I'm not guessing that this is going to bring back a whole lot more revenue. And it doesn't, but it does bring back some. So $250 extra in ticket revenue. Okay, off we go. On to the next problem. Close the 1,200 meters of fencing, 2 pans is shown, stone wall on the north side. Okay, so no fencing on that side. Upper side is north. How should she set the dimensions? She wants to enclose the maximum area. Well, we have to be clever with our algebra here first. The calculus, like on the last problem, the calculus was simple. First derivative set equal to 0. Same thing on this one. Our algebra is where we have to work at this a little bit. So if you don't know what you're doing right away, I suggest you try some number in here. And then after that, try a variable. So let's see, 1,200 meters. Let's say, for example, that here's a stone wall in both cases. Stone wall there, no fence needed. Stone wall at all, no fence needed. Let's say, for example, this was, I don't know, let's guess 200, 200, 200. On our ones we don't know, we call each of those x. So if I want to figure out how much fence was left for this last side, I'd take my total amount of fence, which was 1,200 meters, and I'd subtract 2, 4, 6, I'd subtract off 600. That would leave me 600 remaining for this. Okay. So how could I figure this piece out in terms of x? Well, I started with 1,200. I'm using 3 of those x's. This is 1,200 minus 3x. What's the area? Well, length times width in this case would be 600 times 200. That'd be 12 followed by 4 zeros, 120,000 square meters. Let's calculate the area of this one, which is a variable for the width. Area is length times width, 1,200 minus 3x. There's the length times the width. I'm talking about that whole rectangle there. That's what I want to enclose as much of as possible. A is also equal to 1,200x minus 3x squared. As always, to maximize this function, we'll take the first derivative and set it equal to 0. 1,200 minus 6x. Divide both, set it equal to 0 and solve. 1,200 is 6x. Oh, look at that. X came out to be 200. Ah, who knew? My guess there was actually the one that had the maximum area. All right, so now we can put all the numbers back in here. We know this is 200. We know this is 200. We know this is 200. We've used up 600 there, 1200 to begin with. There's 600 left. By the way, the second derivative here is -6. It's a function that's always concave down. So at my critical point, at x equal to 200, I do indeed have a maximum. I want to see what the question was at the end. Oh, set the dimensions. Okay, so she should make these three sides each 200 apiece, and then that long edge should be 600. Number 3, a grocer. Yes. Again, if something pops up, and I mentioned this yesterday, I didn't today, if something pops up on any of these and you need further clarification, send me something in the chat, and I'll go back and look at these. Grocer wants to place an order. 350 an order, $70 a box per year. Okay, there should be what, 3 numbers in here total? 4,000 boxes. 4,000 boxes flour sold each year. The placement cost is $350 for every time we place an order. And then there's storage cost of so many dollars per box, $70 a box. Okay. And probably get your calculators out and ready again, because there are going to be some things here that I'm more than likely not going to be able to do. What is with Isabel and Tommy? I think you're both working on it. Good. Oh, Connor's here too. Excellent. 3 people are pretty good with their calculators. Good to see. All right. You know, $70 per box for storage. So what I'm going to do again is sort of work this out 2 different ways. I'm going to look at it. Well, how about if I do? I'm going to see number of boxes. Yeah. How about I try 400 boxes per order? Just trying it with numbers and see if it makes sense. And then later on, I'm going to try this with X boxes per order. See if I can streamline this. Well, if we have 4,000 boxes and we do these at 400 boxes an order, that means we need 10 orders every year, right? We get 1/10 of them at a time. If I do this at X boxes at a time, it'll be 4,000 boxes divided by X. There's the number of orders. If I place 10 orders and it costs me $350 every time I place an order, the total order cost then will be 350 times 10. The number of dollars per order times the number of orders. So if I have X boxes in order, I'm going to do things the same way. It's $350 per order multiplied by 4,000 over X orders. And I'm going to try to do this one in my head. I see what, 1, 2, 3, 4 zeros. 4 times 20, carry the 2, 12, 14. So if I did that right, it's 1,400,000. If that's not right, someone let me know right away. So there's the order cost. The other thing that changes is the storage cost. If I order a whole bunch of boxes at a time, then I have to put them in storage, and that eats me alive. So let's see, the storage cost is $70 a box. If I order 400 boxes at an order, what I'll start with is, right after I order, I'll have 400 boxes. But then they'll sell out, and I'll be down to 0. Then I place the next order. I'd be a few weeks later, there's the next order, down to 0. Next order, down to 0. Now, I'm not using all of that storage all the time. I'm only using about half of it. Sometimes I have nothing in storage. Sometimes I have 400. So in order to find out my average number of boxes in storage, I take whatever the number of boxes is and divide it by 2. So 400 over 2 will be the average height of this curve, if you want to think back to what we did recently, or the average number of boxes in storage. The average number of boxes in storage in this case is however many I order at a time divided by 2. So there's a number of boxes in storage if I have 400 boxes per order, or if I have X boxes per order. For every box in storage, it's $70. So this would have been 200 times 70. And this one is going to be 70 times X over 2, which is 35X. Okay. All right. Those are the only two things that vary as far as the cost is concerned. The flour costs me so many dollars a box for sure. But that doesn't matter depending on how many orders I place. That's just that flat non-variable cost. So here are my two variable costs. As X gets big, the storage cost gets bigger, right? And as X gets big, the order cost gets smaller. So there's a fight between the one and the other, and we want to balance that out. We want this variable cost function to be what we get when we add those two together. We want that to be as small as possible. So we have 1,400,000 over X plus 35X. Okay? Find the first derivative. Well, I could have rewritten this if I chose as X to the minus 1 to make the calculus easier, and I'm going to do that. So taking the derivative negative 1,400,000 X to the minus 2 plus 35. Negative exponents are handy in calculus, but they're not that easy to work with algebraically. So let's set this back to our more comfortable position. 1,400,000 over X squared plus 35. Whoops, don't forget the negative sign. That's what we want to set equal to 0. I'm going to bring this over so I don't have to work with negative numbers any place in this problem. And then I think 2 steps of algebra later, I'll be in pretty good shape. Let's see, multiply both sides by X squared. Allows that to cancel. Divide both sides by 35. And I have a calculator here I can use for that part. I'm a little worried about the square root. Let's see, 1,400,000 divided by 35. Oh, that comes out nice. 4 followed by 4 zeros. So 40,000. And that one I can't take the square root of, not too bad. That's 200. I imagine that it would be important if this were a little more advanced class to take the second derivative and make sure that the point I found is a absolute minimum, or absolute minimum in my interval and not a max. I think I'm going to let that one go for now. So let's see if we can go back and answer the questions. Find the, okay, did that number of boxes per order? Okay, I did that. And now I'm going to sort of wrap everything up. I remember in final exams in the past, this question I don't think was ever worked all the way through. They might have been write an expression that has the total reorder cost. It'd be something like this, or find the expression that gives the total storage cost, be like that, or find the expression that gives the total variable cost, that plus that. I don't recall this ever going from the beginning to the end on the final exam. But let's do it anyway. Let's see if we can make some sense of this at the end. Okay. So there is our 2 variable cost. Here is the order cost, right? Yeah. So 140,000 over 200. Those cancel out. That would have been $7,000. Okay. And if I plug 200 in here, that one is also $7,000. And that's a nice little check on this one. I mean, we've worked problems like this 7 or 8 times. always works out that the minimum total cost is when those two are equal to each other. So there's a nice little extra check. If you have time on the final, and you will, for the most part. Okay, got it. On to 31, the marginal cost is, this is one I covered on the very last activity. So we'll do it one more time here, I guess. If you have Monday's notes, Tuesday's class notes with you, I think this is the exact same problem as well. The numbers look so familiar to me. Let's see what we got here. In the marginal cost, let's find the cost. Okay. Marginal cost function are typically downhill functions. We want to figure out how much it's going to cost going from 50 a month to 75 a month. We're talking about that much area. Remember, this is dollars per unit manufactured, and this is the number of units manufactured. When you multiply those units together, you get strictly dollars. The area under the curve measures dollars. And since this is a cost, a marginal cost function, it'll be the dollars of cost. That's what we want to find. So let's see if we can find the area under the curve. It goes from 50 to 75 of the marginal cost function, 125 over x plus 5 dx. And again, I got caught up here with one of these that would technically require the chain rule. And there won't be anything like that, I promise you, on the final exam. But you should understand how I was able to set that up. This is really a great final exam question. How do you interpret a definite integral? How do you take a marginal cost and turn it back into a cost function? So this would be a great question on a final exam to just stop right here. I'm gonna go through the rest of the steps with you just in case. This one again is an antiderivative you can't do because you haven't had the integration by substitution, but I will just give it to you. It's 125 natural log x plus 5. And you can check this one out. The derivative of this is 1 over x plus 5. So 125 over x plus 5 is definitely correct. Evaluate that between 75 and 50. So we have 125 natural log of 80 minus 125 natural log of 55. Grab out your calculator, someone. Do that subtraction for me. This will be measured out as thousands of dollars per month. Dollars per unit. Thousands of dollars per unit. There we go. So 125 natural log 80 minus 125 natural log 55. $46,837. Good. Again, the answer is checkable on the answer key. If anyone else got that, I mean, it seems reasonable to me. I've got a natural log of a little bit bigger than 1. Talking about an E. Yeah, seems reasonable. All right, now we have part B, and here's the one that, again, so many of you screwed up on the test. We're going to have the fixed cost is $400,000. So we want to come up with the cost function. I know cost function is the antiderivative of this plus some number k at the very end. And that k is not the fixed cost. Thanks, Con, appreciate it. The k is the number that when we plug in 0 makes this whole thing on the right equal to $400,000. So I'm going to set this 400. Remember that cost is in thousands of dollars. So 400 equals 125 natural log of, plug in a 0 here, 5 plus k. So solving for k, again, the calculator here is going to be handy. We have 400 minus the natural log of, minus 125 natural logs of 5. So what does that number k turn out to be? Natural log of 5 is around 2. It's got to be a positive number still, I think. So if someone would be so kind, 400 minus 125 natural log of 5. Again, we know the initial condition, when we plug in 0, we have to get back 400. So what is 400 minus the natural log of 5, so we can finish this problem up and go on to the next one? $198.82. Okay. Got it. So there's my original function. Again, the derivative of this is right there. And when you plug in 0, you get 400. Nice. And it's been duplicated. I love it. On to problem 32. Find each antiderivative. All right. Here we have several uses of the power rule. A couple of uses of e to a linear power, and then those tricky ones where you have a single x in the denominator. So I'm going to rewrite the first one. I'm going to rewrite this one as 3 separate ones. X to the 1/3 dx minus 5 integrals 1 over x dx plus 2/3 integrals x to the negative 1/3 dx minus e to the x, antiderivative of e to the x dx. So since there were 4 terms separated by pluses and minuses, I rewrote these as 4 terms separated by pluses and minuses. If they had a coefficient, I moved the coefficient in front. So here we go, the power rule. Let's see, keep the x, raise the power by 1, multiply by the reciprocal of the new power. Done. Minus 5. This is the one case where the power rule doesn't work. Natural log absolute value of x plus 2/3 a constant multiplier. Keep the x a little later on. Raise the power by 1. That becomes 2/3. Multiply by the reciprocal of that new power, 3/2. And then finally at the end, minus the antiderivative of e to the x is e to the x. And then finally, don't forget the plus c at the end. And I didn't notice so many people doing that. So let's go back to our more typical form. And I found that on the final, most often these are right back in root and radical form. So let's get used to that. Two thirds and 3/2 cancel. So that would be cube root x squared minus e to the x plus c. Problem 1 is done. Any questions on that? Hopefully not. That was a nice problem. It illustrated really 3 things: the power rule, the 1 over x antiderivative, and then the e to the x. So this is sort of the basics. This is what we did the first day when we came back after exam number 3. On to number 4. What am I saying? On to letter B. Here we have e to a linear power. So I could rewrite this if I chose as 120 antiderivative of e to the 0.32x dx. If I were to take the derivative of this, I would bring down the derivative of the power as the multiplier. Since I'm doing antiderivative, it's going to be the opposite of that. I'm going to bring down the reciprocal of that as a multiplier. Remember, on the e functions, we always keep the power exactly the same. I can do this on my calculator. 120 divided by 0.32 is 375. Nice. So 375 e to the 0.32x plus c. There's the antiderivative. On to the next one. Here we have two functions multiplied together, and we didn't learn anything about a product rule as far as antiderivatives were concerned. In fact, there is no product rule for antiderivatives. So if you find yourself in a product situation, unproduct it or multiply it out. So I'm going to FOIL those two things out. We would have a 15 minus 5x plus 3x squared and minus x cubed. Using whatever technique you like to use to multiply two binomials together, you should get those three terms if I did it right. And you did it right. Okay, off we go then. Separate integrals. Antiderivative of 15 is 15x. Bring down the minus, bring down the 5. It's a multiplier. Keep the x, raise the power by 1. Multiply by the reciprocal of the new power. There's term number 2. On to number 3. Plus, keep the 3, keep the x, raise the power by 1. Multiply by the reciprocal of the new power, 1/3. And then finally, the last part of the antiderivative, keep the x, raise the power by 1, multiply by the reciprocal of the new power, and to finish the problem, tack on the plus c. Now let's make this look as pretty as we can. 15x minus 5 halves x squared plus x cubed minus 1/4 x to the 4th plus c. And if I take the derivative of this, I can check my work easily. The derivative of 15x is 15. The derivative of that, the 2's will cross cancel, minus 5x, 3x squared, no doubt. Bring the 4 down, cancel it with 1/4, 1x cubed. Derivative of every constant, regardless of what that constant is 0. Next on our list to find the antiderivatives. Well, again, we have a quotient rule here, and the quotient rule is not going to work. So we're going to have to do the quotient part first. And since we're dividing by a monomial, let's make sure we do that for each of the terms. So rewrite this with each term divided by that monomial. So my original polynomial, 5x minus 6 plus 7x squared, I separated into 3 bits, each divided by the x squared. So let's see if I can simplify these a little bit. 5 and a 3, there's not a lot I can do. That would be a 5 and a 3 out front. X over x squared, that's 1 over x. There's the first part. On to the second part. Minus 6 over 3 is a 2. I'll bring that constant out front. X is in the denominator, x to the minus 2 dx. There's the second part. Now the third part, 7/3. Oh, nothing left but 7/3, I guess, huh? Dx. Looks like I'm ready to go. 5/3 natural log absolute value of x. Keep the minus 2, keep the x, raise the power by 1. Multiply by the reciprocal of that new power, and the derivative or the antiderivative of any constant is that constant times x. Now let's make this as pretty as possible. 5/3 natural log absolute value of x, minus minus cancel, plus 2 over x plus 7/3 x plus c. So we got to work on a few things on that one. First off, derivative, or first off, division, and then we got to play around a little bit with the power rule, and a little bit with the 1 over x. What's that one? And then some students mess that up a little bit on the last exam. Also, what do we do with the antiderivative of a constant? And we tack it on. With those done, then the next 4 should go fairly well. We need to do the antiderivatives. The antiderivatives here look easy. I'll plug in the lower number, plug in the upper number, see what we get. As always, I want to encourage you to work these problems through on your own. And if you get stuck, come back, maybe watch this video one more time if there's something that you didn't understand. I noticed that we're into the more recent stuff now, aren't we? Boy, that didn't take long. So let's see, the antiderivative of that one is going to be x cubed minus x squared, right? Antiderivative of 3x squared is x cubed. Antiderivative of negative 2, sure, take the derivative of this 3x squared, the derivative of that 2x. I like it. So I've already found the antiderivative. Evaluate that from 3 to minus 4. If I plug in 3, I get a 27 minus 9. 27 minus 9, I believe, is 18. Someone make sure I'm not screwing this up. If I plug in a minus 4, I get a negative 256 minus 16. I get a negative 272. And when I take that subtraction, 18 minus negative 272, I get 290, if I did my calculations right. If someone would like to check my work, I'd appreciate that. Or if you have the answer key open, you want to see if that's the right answer on the end. Hey, that works too. So I took the antiderivative, plugged in the top, plugged in the bottom. On to the next. So I'm going to work on the antiderivative right away. 1200 is a constant multiplier. I'm going to keep e to the 0.16t. I'm going to multiply by the reciprocal of the derivative up there. So let's see what we get on that calculation, shall we? $1,200 divided by 0.16 is 7,500. 7,500 e to the 0.16t evaluated from 5 to 0. So let's see, we'd have 7,500 e to the 5 times 0.16 would be 0.8. And here we have 7,500 e to the 0. So this one down here is 7,500. The top one's got to be quite a bit bigger. I think I can do that in the toolbar here. Looks like that's 12365. Subtract 7,500 from that. 4865. And again, this is a multiple choice format test. They're not going to worry. You're not going to have things that round really close, have 5 answers that are really close, and if you make a rounding error, you're going to mess it up. We're not trying to trick you on this with rounding. We just want to make sure you understand how these are going to work. Now, if you did something dumb on this one, like you by 0.16 instead of dividing, sure, that's one of the answers that's going to pop up. If you added 1 to the exponent, yeah, that's probably going to be one of the 5 answers. That's an incorrect answer as well. But as long as you understand, closer, the basic ideas here, you'll be fine shape. Let's see, I'm going to work on the antiderivative of that next one right away. And here's where I'm definitely going to need a little help on the calculator because my search bar doesn't do this one very good. So the antiderivative, let's see, I keep the 12, I keep the x, I raise the power by 1, 2.2, and multiply by 1 over 2.2. That one's going to be messy, I can tell already. The next one, I keep the negative, I keep the 4, I keep the x, I raise it to the 1.2, and multiply by the reciprocal 1 over 1.2. That's my antiderivative. Well, you got a different number for the top? Oh no. Well, whatever the answer key has on that one, I'm gonna go with that. And if we need to straighten it out later, we can straighten it out later. So 12 divided by 2.2. 12 divided by 2.2 is 5.45. X to the 2.2 minus 4 divided by 1.2 is 3.33. We're going to evaluate this, and here's where I'm going to definitely need some help. I'm going to evaluate that from 8 to 0. I'll do the 0 one. That's an easy one. 0, 0, that one's 0. So if a couple of you would take your time on this one, plug in the number 8 for x. Let me know what you get. So there's a chance that I screwed that last one up. That's the trouble with putting things in the search bar. Thanks, Tommy. So I'm going to go with what both you and Connor had, the 1669155 for the top. And there's only so much I can do in a search bar. And sometimes I don't put the parentheses in the right spot. I suppose that's what happened. I should put parentheses around. Yeah. So let's go back on that one, and Connor and Tommy are right. So how about when we plug in 8 in this one? $48, okay. If anyone else picks anything differently. Yep, doubled, nice. On then to letter D, which is one I think I can do without the aid of the calculator. So what I see on letter D is something that has a coefficient, and if I get that coefficient out in front right away, it's going to help. So this is 3/5 times 1 over x dx. Antiderivative is 3/5 natural log absolute value of x, and that's going to be evaluated from e to 1. Okay, if I plug e in here, the natural log of e asks me e to what power is e, and that's the first power. So if I plug in e here, I get 3/5. If I plug in 1, it's natural log of 1 asks me e to what power is 1, and that's e to the 0th power. So that's 0. 3/5 minus 0 is 3/5. Problem 34 is a conceptual type of question. We have a definite integral between 0 and 4 over our function, and we have to realize that that's just the area under the curve between 0 and 4. So since we don't have a function given there, we're just going to assume that each of those boxes is 1 high and 1 wide. There's no scale there. So what I'm going to do is count the total area. So let's see, 1, 2, 3, 4. It looks like it goes straight across here till there, and then it goes up. So that's the area I'm going to count, and here's how I'm going to count it. Each of those squares there is 1 square unit, so it's like 1, 2, 3, 4, and that triangle is exactly half of that next square up, so that is 4.5 square units. How about from -5 to -1? Okay. Guess I can use the same graph, huh? 1, 2, 3, 4, 5. There's -5. The graph is -1. The graph comes straight over here. And then it veers off at a 45-degree angle, huh? Let's see, 1, 2, 3, 4 goes up 4. 1, 2, 3, 4. Down there. All right. So now we're going to try our best to figure out what. Oh no, it goes up quicker, doesn't it? 1. No, we're good. 1, 2, 3, 4, 5. Ah. There we go. So what I would do is probably break it up into shapes like that and start counting the full squares. Let's see, 1, 2, 3. There's 1, 2, 3, 4. There's 4 in that column. There's a triangle here that I'll count later. Underneath here, there's, let's see, 1, 2, 3, 4, 1, 2. I might have messed up this a little bit. I have to have another line in there. There we go. Let's see, 1, 2, 3, 1, 2. No, that was right before. 1, 2, 3, 4. Yep, 1, 2, 3, 4. I'm going to count those, and then I have this triangle left over, and that triangle is 1, 2, 3 tall and 2 wide, right? No, 3 wide. Oh, now I'm confused. 1, 2, 3. 1 to 5. So 1, 2, 3. 1, 2, 3, 4, 5. 1, 2 is where it jumps. 3, 4, 5. Okay. Dread. I had the graph drawn right the first time. Ah. All right. There. Now I have it. Okay. That makes it. Yeah, that makes it way easier. So I have those 4 at the bottom, and then I have that triangle here, and that triangle is 3 tall and 3 wide. 3 tall, 3 wide triangle, 1/2 base times height. That would be 1/2 times 3 times 3. That would be 4.5. So I have 4.5 in that triangle, and then 4 more below it, 8.5. Yep, thanks, Tim. Find the average value of that function from -2 to 4. Okay. Well, the average value is 2 calculation steps. The first one, you find the area under the curve, and then you average it out by dividing by whatever the length of the curve is. So we're going from a -2 to a 4. That's 6 units wide, so it's 1/6. Take the antiderivative of 25x plus 3e to the 0.5x. 1/6 of, let's see, that's 25 times 1/2 x squared plus 3 times 1 over 0.5 e to the 0.5x. 1/6 of 22/2 x squared plus 6e to the 0.5x, evaluated from 4 to -2. Okay. And I'm going to allow you to finish that one out. I'm starting to run a little bit shorter on time than what I wanted to. I don't want to drag this out. That's the main lesson there, right? Find the function for which that's true, and f of 0 is equal to 20. And again, this is one of those, just to make sure that people don't mess up the final as they messed up the, the one question on the last exam. Just because the initial condition has a value, that's not necessarily the value of the constant that's at the end. So we know the derivative of the function is that. Oh gosh, this one ties in really nicely with 35, doesn't it? So we know the antiderivative has to be 25 halves x squared plus 6e to the 0.5x plus some constant k. So we're given the antiderivative, so the original function has to look something like this. The question is, what is k going to be? We know when we plug in 0, we get 20. So 20 has to equal 25 halves times 0 plus 6e to the 0.5 times 0 plus k. That's 0. That's 1. 20 has to equal 6 plus k. So k must be 14. So one more lesson on the initial condition. Don't just guess that number to be the 0 value. Given the graph below, find the mathematical expression that'll find the area of the region. Okay, then find the area of that region. Oh, I don't know what, oh, yeah, I'm given the equation. Okay, sure. So the area will be the antiderivative, or the definite integral, I should say, from 1 to 3 of whatever my function is, d whatever my value is, my variable. In this case, it's that. There is the mathematical expression that finds the area of the shaded region. It's a definite integral. It'll spit out a number of square units. So they want us to do that. 1/2 t squared plus e to the t is the antiderivative. Evaluate that from 3 to 1. And I'm just going to let that one go as well, assuming that everyone can put the buttons on the calculator. If you want to check the answer, that is in the answer key that I provided. Find the area of the region bounded by the two graphs. Okay, this one was taken directly from an activity we did just a little bit before the exam. I think it was the 2 days before the exam. We did this one, and then we did the Gini index and the Lorentz curve the day before. So this was 2 class periods before we were learning about the area between curves. First thing we have to do is find out where these things cross. And since we're only given 2 functions, there's not a whole lot to do except for set those functions equal to each other. Have to find out if they cross first off. And if they don't, we just throw up our hands and say it's probably an infinite area. All right. So we're going to set that equal to 0 since it's a polynomial function, x cubed minus 6x squared plus 8x. Then we're going to factoring an x out, x squared minus 6x plus 8 equals 0. I need 2 factors of x that add up to a minus 6, x minus 2, and x minus 4. If you can't solve that by factoring, the quadratic formula works just fine. So my 3 places where that's equal to 0 are at x equals 0, x equal 2, and x equal 4. I have 2 separate regions, one of them between here where the two graphs cross, and one in that interval from 2 to 4 where the 2 graphs cross. I'm going to highlight which of these is which. This is F. And this is G, because that's going to pay dividends a little later. So the first interval goes from 0 to 2. I'm going to take my upper function minus the lower function. I'm going to look at x equals 1 to see which one is above the other. Again, between 0 and 2, at 0 and at 2, they're equal. Between 0 and 2, one of these has a higher value than the other. If I plug in x equal 1 here, my g value is equal to 1. If I plug a 1 in here, I get a 1 minus 6 is negative 5. Here, my f value is a 4. 4 is bigger than 1. So in the first place, the first integral is going to go like this. This function minus that function. And when you work that out, you'll find the area of the first part is 4 units. Okay, now the second definite integral. Here we're going from 2 to 4. Again, these two graphs crossed at x equals 0, x equal 2, x equal 4. Now I'm going to choose a number in between 2 and 4. I'm going to choose x equal 3 and see which of these is the bigger. When I plug in x equal 3 here, I simply just get 3. If I plug 3 into here, I get 27 minus 54, which is a negative 27, plus 27, which is 0. So here I get this one is 0 and that one's 3. This is the bigger of the two. X minus the smaller of the two. X cubed minus 6x squared plus 9x. And I ran a little short of room, but there should be a dx at the end of that one. On this one, I would probably combine these two, make it be an 8x. I'm going to trust that you can use the antiderivative rule on this one and come up with the area equal to 4. On this one, you don't forget to distribute the minus sign, and if you distribute the minus sign correctly, you should end up with a minus x cubed plus a 6x squared minus an 8x dx. That one should look just the opposite of this, and it does. And again, when you finish this one out, you should find that this area is also 4 square units. So the total area between those two curves, 8 square units. Find the area bounded by those 3 curves. Okay. So now we're upping the game a little bit. We have a little more understanding needed to figure out where we're going on the next one. More than 2 equations. We have x equals negative 8, x equals negative 2. There's negative 2, 3, 4, 5, 6, 7, 8. There's negative 8. There's 2 of our fences. G of x is 3 over x. Let's see, so that's got to be 3 over x and like this. It's going to be something like that, I guess. And then x minus 2. X minus 2 probably looks something like that. So now, the most important thing is to figure out where f and g cross. We already know we have a gate over here at negative 8 and a gate at minus 2. Now, if these two cross in between here, then we got a little work to do. Then we'll have a couple of areas. But that's the most important thing. Where do those two cross? Where is 3 over x, my g function, equal to x minus 2, my f function? Multiply both sides by x. 3 equals x squared minus 2x. Quadratic equation. 0 is equal to x squared minus 2x minus 3. Let's factor that out. X minus 3, x plus 1, at x equal to 3, and at x equal to minus 1. Those are the 2 places those cross. Phew. Neither of those places are in between this line, which is negative 8, and this line, which is x is minus 2. So in that interval between minus 8 and minus 2, one of these is always bigger than the other. There's no switching places. Okay. But it's important to know where your 2 non-linear functions. It's important to know where those cross, your non-trivial functions, I should say. So now we know we are set. We have the 2 fences. We have x is negative 8. We have x is negative 2. I can boldly go, whoops, I want the bigger number at the top, boldly go there. Now again, my 2 functions were x minus 2 and x over 3. I'm going to choose some number that's in between those two. I'm going to let x equal negative 3 and plug it into both and see which one is bigger. If I plug it in here, I get negative 3 minus 2 is a negative 5. If I plug it in here, I get negative 3 over 3, which is a negative 1. That is the bigger of the 2 functions. So when I go to set up my integral, it's always the bigger minus the smaller. Whoops, had that one wrong, didn't I? 3 over x. Okay. Regardless, when I plug a negative 3 in here, it's still minus 1. So now it's my bigger minus smaller. 3 over x minus, in parentheses, x minus 2 dx. I'm going to carry this one a little further than the last because there's a couple steps here that I want to make sure everyone catches. Okay. First off, don't forget to distribute the minus sign. Oops, I almost screwed it up. Now take the antiderivative, 3 natural log absolute value of x. Those absolute values are going to be critical in this problem. Minus 1/2 x squared plus 2x evaluated from -2 to -8. And I'll trust you to run through your calculators and get that one. The Lorenz curve is given. I think this one was taken directly from the one of the more recent activities, probably the one before the last test. I think I used that same Lorenz curve. So the first part is find the Gini index. So the Gini index is going to be the area between the two curves. The top curve is going to be the curve of equal distribution of resources. The second curve is going to be the actual distribution of resources. So here I have a 2 out in front, integral from 0 to 1, 0% to 100% of the population. X is the equal distribution. We're going to subtract off from that the Lorenz curve, 1/2 x plus 1/2 x squared dx. I'm going to bring the tube in a little later. I like to save it for the end. Antiderivatives of distribute this through here. X minus 1/2 is 1/2 x. So distribute the minus sign, minus 1/2 x squared dx. Now I guess I could distribute that 2 back through here and have x minus x squared. That'd be sort of pretty, wouldn't it? But let's not. Let's continue doing the way we've been doing. So we have the 2 multiplied out front. Antiderivative here would be 1/2 times 1/2. That would be 1/4 x squared. Here we keep the 1/2 reciprocal. The new power makes this 1/6 x cubed, evaluated from 1 to 0. At this point, plug in the 1, you get 1/4. Plug in the 0. No, plug in the 1, you get 1/4 minus the 6. Plug in the 0, you get a 0. So it's 1/4 minus the 6 times 2. Grab out the calculator and see what you get. That one that was maybe about a 60% right one on the last exam. I think a lot of you forgot to multiply through by 2. I saw a lot of answers that were half as big as they should have been. And then I also saw a lot of ones where I'm guessing you forgot to subtract it off from x and you just did the 1/2 x plus 1/2 x squared. Those seem to be, and again, I didn't look at all the wrong answers and tally which ones were done incorrectly, but I just remember there were like 5 popular answers. The most popular was the correct. I think the second most popular was the one where it wasn't multiplied by 2. And the third most correct was where the number was about half as big as it should have been. What wealth of the population do the bottom 80% of the population control? Well, we get that from the Lorenz curve. We plug in 0.8 in the Lorenz curve. I thought we did this one really well on the last test. So that's 0.4 plus 0.32, 0.72, 72%. Quite a bit. Part C, country B had a Gini index of wealth of 0.8. The one that we looked at before was quite small, quite a bit smaller than that. Since the Gini number was bigger on country B, country B had a less equal distribution of wealth. Our country A had a more equal distribution of wealth. Problem 41, the sales rate of Tesla automobiles since 2014. Boy, I came up with this one, I think, a couple of years ago, and there's been some data since then. I should see how well this still models the current situation. There were the one car company that sold more cars in the first quarter this year than they did the previous first quarter of last year, and that was bucking the trend. Every other gas automobile sold quite a few less. In fact, 2019 saw the number of internal combustion engine vehicles decline and the number of electric vehicles go up a lot. And it's the trend, by the way. There's a guy I like to listen to called Tony Seba, who's a guru of disruptive technologies. And his first slide shows a picture of New York City. I think the year was 1912. Picture New York City, and there's nothing on the streets except for horses, and there's one car. And then 1922, same picture, same setting, big picture, New York City, all cars, one horse. So, like in 10 years, things switched a lot. Anyway, Tony Seba says that by 2025, we will have a electric vehicle that'll travel 200 plus miles on a charge and be for sale for about $15,000. And he says at that point, no one will ever buy an internal combustion engine again for a number of reasons. The most important reason is they're cooler. They're more fun to drive. The second is they're way cheaper to operate. Once the price comes down, it's going to, you can see it. You can see the writing on the wall. So anyway, here we're going to be given the sales rate. Find the sales rate at the start of 2014. Well, the sales rate is given here. So the sales rate at the start of 2014, where T is the number of months since the start of 2014. Now at the start of 2018, let's see, there's 12 months in a year. So I guess we'd have to calculate S prime of 48. Plug that in your calculator and off you go. Find an expression for the total number of vehicles sold T months after the start of 2014. Well, here's your sales rate. 0 starts 2014. We're talking about T months after 2014. This is vehicles per month, and this is the number of months. The area under the curve is the number of vehicles. So the number of vehicles sold would be from 0 to T of S prime of T dt. Area under the curve. 42 sort of piggybacks right on this. Area under the curve means what? In this case, we have the water usage rate. And notice how that spikes right around 8 o'clock in the morning. Typically, that's when people are up from their slumber and turning on the shower and washing their face and getting their coffee ready to go, all sorts of uses of water. Early in the morning, that's by far the busiest, the peak time for water usage. And notice before that peak, there's quite a valley there where everyone's asleep at 2, 3 in the morning. And it sort of varies a little bit as the day goes by. So I want to note that on this axis is I want to get the units right here, thousands of gallons, so K gallons per hour. And down here is the number of hours past midnight. So the squiggly line is the water usage rate, how many gallons per hour. The area under the curve is the combination of these units times those units. Thousands of gallons per hour times hours is thousands of gallons. So anything under the curve measures thousands of gallons. Anything curve related is the usage rate, thousands of gallons per hour. What does the shaded region represent? Number of thousands of gallons consumed from, let's see, 4 hours past midnight, from 4 a.m. until 4 hours past noon until 4 p.m. Thousands of gallons of water consumed. Not the usage rate, it's not gallons per hour. The squiggly line, this squiggly line gives us the water usage rate. The area is the number of gallons. Estimate the number of gallons that are used from 4 a.m. until noon. All right, so I'm going to graph this a little more carefully, and I'll show you how I would have guessed it. So 4 a.m. is right about there. Noon is sort of back in this little bit before the peak. So 4 to noon, that's an 8-hour stretch. Right? And I'm going to sort of take the bumps and the hills and the valleys out of that graph. I'm going to try to draw a line across here using those fences. Try to draw a line across here so that this area where the usage is above the average and the area where the usage is below the average, so those two things sort of balance out. I have a marker here. I'm going to try to draw on my paper, see how well I can do. Yeah, that seems to be about right. I would guess that on average, it would be right about, I don't know, average height is probably somewhere around 48,000 gallons per hour. So the total, is that what they want? What I wanted? Yeah. So 48 multiplied by 8, whatever, that comes out to be that many thousands of gallons. Next, estimate the average value of the function in this shaded region. Okay, so I'm going to do the same thing here. Move my shaded region to include that little dip. There's my shaded region. I want to, this is a fence, this is a fence. I want to draw a line across here so that the area up here sort of fills in those little bottom lines. I want to take the peaks and the valleys out of that function that has a lot of different variation and replace it with a straight line across. Again, I'm going to do my best to see where that would be and then draw a line across there. That looks a little high. I would guess maybe that's right around 42,000 gallons per hour. Again, that's just an approximation. If I wanted to expressly write what that was, it'd be the antiderivative from what, 4 to 16, 1/12 of that, of whatever my water usage gallon rate was, R of T dt. That would give me exactly what the average water usage rate was. In the context of the problem, what does that represent? That would be, let's see, area under the curve for part D. So part D, the definite integral would be the water used, total numbers of thousands of gallons used. So here we are on part D now. There's no multiplier out front. That would be the thousands of gallons used from 10 a.m. until 4 p.m. I do remember grading through your work on some of those activities, especially the ones with the electricity, and the units just weren't what I was hoping they would be. You write a calculus expression that would represent the average water usage rate for the entire day. Okay. 0 to 24 is a 24-hour period. R of T dt. Without that out in front, that would be the total used for the whole 24 hours. Divide that by 24 hours, that's the average water usage rate, and that would be measured in thousands of gallons per hour. It would take away those hills and the valleys on the water usage rate that was there and replace them with a line straight across. That line would be that average height. There's the supply and the demand curve, and we did this exact problem on Monday in class, On Tuesday. When do we have class? Do we have class on Tuesday? Yeah, Tuesday in class. We did this exact problem. Nothing has changed. So I'm going to allow you to either go back and watch that again or figure that one out. I don't want to cover it in the last few minutes because this was the same thing we did then. And that takes us through. It took a little over, I got a late start today too, though. I was distracted for a while. Anyway, it took about an hour and a half again today. But we've been able to cover pretty much every question on that review packet. And my suggestion again is to go back, look at the questions, look at them maybe with a little more relaxed eye. Get stuck on something, fast forward to the videos where I cover it. If you're still stuck on something, send me an email. We can either chat via Blackboard Collaborate. I'll try to make myself available probably from 5 until maybe around 9 this evening. That way, if there's some last minute questions, you can ask me. My 3:45 p.m. class, my late class, has their final exam scheduled for 7:45 tomorrow morning. So bright and early, drag yourself out of bed, sit for the final. My suggestion is you do a little studying yet this afternoon, so we're feeling somewhat confident. Get a good night's sleep, because that'll really help as well. Don't pull an all-nighter. That never works on an exam like this. Any more questions? Okay. As I said, I'll have this the timestamps on this probably around 5 or so, and I'll try to keep myself available. I'll be in and out, but I'll try to keep myself available from 5 until 9 this evening. Good luck with your studies.